Hi everyone, welcome back. Jason said the last one was our last video we live
You can
because
tell how excited I was for it to be the last
yeah,
one.
we were kind of hoping to be done because it is Thanksgiving and here we are at Olin working hard for you. But anyways, we thought it'd be worth showing you some examples of using code to do validation. One of the things we really want to encourage you to do is to actually take advantage of the fact that you've got this sort of core model and then write code around that model that allows you to do different types of validation. So we're going to show you some examples and then talk to you about what we sort of get out of them. So the first set of examples we're going to look at is actually some raw results plots. So we're going to look at both the hopper and also at the skateboard and try to see what we can say from these different types of validation. So we'll start by plotting raw results. When we say raw results, what we're after is just like, what is it that ODE 45 produces, right? So let's try that. I'm going to get an error because I'm not, oh, I did get an error. How
about
exciting.
That? Whoa, look at that.
Wow. All right, so let's take a minute to look at this. So we'll look at the code in a second. So here is plotted position versus time of the rod and the reaction mass, and it's labeled raw results of ODE 45. So this is like literally what the Y position of the ring is and what the Y position of the rod is. Actually, I guess the rod is red, the ring is blue. As a function of time, it's just spit out by ODE 45. And as you can see here, there are a couple things that are going on. You can see that, first of all, the rod is actually appears to be oscillating more than the ring. You can see the ring lifting up off the ground, and then once the ring has gotten a little ways past the rod, that's when the rod starts to lift off the ground. So this sort of looks like we might expect it to. A couple things to notice about the way that we've actually put this code together. One is that we've actually up here specified a whole bunch of the parameters. And the reason that we did this is so that we actually, if we produce a bunch of these plots and save them or print them out, we actually know what it's a simulation of, right? Because it's so easy to get a whole bunch of different results and lose track of what they mean. So taking the time to actually put a label on, taking the time to label your y-axis and your x-axis, taking time to put a title on is useful. And I think in this case, you kind of get something from these raw results, right? Should we look at the code for this, or is this not worth looking at? Probably not worth spending very much time on.
Let's take a look at it.
So here's the code, right? All we're doing is setting it up. We're calling a function that's the ODE 45 function, and then we're doing some plotting. And notice here that we're actually really explicitly putting on this text that has to do with what all the parameters are for the system.
And that's it.
That's it.
All right. So what else can we do? We've got the raw results. Do you want to take a look at an animation?
Why don't we look at the skateboard raw results
for
first?
the same thing? Okay. So let's go to skateboard code here and skateboard raw results. Skateboard raw results plot. Okay. So
right. So this is doing basically the same thing. So notice that we haven't really specified as many parameters here because there's only one that we're dealing with, which is what the initial velocity is going in. So there's a bunch of stuff with L and so on that we haven't labeled. And we haven't really labeled the y-axis because it has both R and theta plotted on the y-axis. So R is blue and red is theta. So what does this mean?
Well, let's see. So our theta is the angle of rotation, starts out... Well, let's see. It starts out constant here, so that means the ramp is not rotating initially.
Right. And it looks like it drops.
So it starts to rotate one direction.
So does that mean it goes like down, and then does it go down the other direction, or does it just go back to being up?
Should go back to its original position.
Okay.
Right?
And R starts at -2, goes up to. So 0 is the middle of the ramp. So this is the guy going up the ramp at 0. Yeah, okay. So at 0, the rider passes the middle of the ramp. At that point, that's where theta starts to change, where the ramp starts to move, gets partway up the ramp, but doesn't get all the way to +2, and then kind of rolls backwards. So it looks like this is an unsuccessful.
So it's a roll off.
This is a roll off to the left. Okay. The reason why we sort of exposed you to our trying to figure that out is that it takes a long time to figure this out. Like, this is a super impenetrable plot, I think. Even though it's a simple condition, like figuring out what it actually means physically, I think is hard, and that's part of why it's often not the best plan just to make these kind of raw results plots. For the hopper, it's not too bad, but for this thing, for the skateboard, it's virtually impossible to interpret, I think.
Yeah.
So let's look at some other stuff.
Okay.
So let's see, how about some animation? We already looked at this animation once, so let's look at the hopper animation, right? Just for the sake of old times, right? So there we go, hopper animation. We saw this. You're probably not saying ooh and ah quite as much now
It's still pretty cool.
as you did when you saw it in class in the auditorium, just because that was like, it was like the first time, and the first time is always just magical. I'm sorry.
Not going there. Not going there.
So anyways, but I guess the point here is this doesn't actually tell you all that much.
Yeah.
It doesn't really tell you anything that the raw results plot tells you. Doesn't, other than maybe you can look at this and say, wow, that doesn't actually make quite as much sense as I think it ought to. So certainly the fact that it keeps on oscillating this exposes a little bit more, but maybe not the most useful thing in the world.
How about the skateboard?
Okay. So a skateboard validation thing. Skateboard animation validation. Here we go.
Ooh, look at that.
Ooh.
Now that's cool.
Oh.
Are these the same parameters?
Oh.
Yeah. Oh, roll off to the left.
Yeah, that went off to the left. Yep.
Huh.
So that I think actually makes a whole lot more sense than that plot we were looking at.
Yeah, it's
Right.
easier for me.
So I think this is an example where the animation does give you some useful insight that maybe the raw results plot doesn't.
Yeah.
All right, so these things that we've just been doing, like looking at the raw results plot, looking at the animations, those are pretty much in kind of the qualitative space, either qualitative experimental or kind of qualitative limiting case. They're both kind of in that space. Let's try to get a little more quantitative. Why don't we do some energy conservation, right? So let's go back to look at the hopper. So we'll look at hopper energy conservation check. So, whoa,
Ooh, look at that.
there's a lot of stuff there.
All right.
So what's going on here? We have the kinetic energy of the rod, the kinetic energy of the reaction mass, which I think is the ring, potential energy of the rod, potential energy of the reaction mass, potential energy of the spring, and then the total energy.
Okay.
Okay, so we've got initially a lot of energy is stored in the spring, it looks like, right? And actually nothing else had, the ring has some net negative potential energy, rod has zero potential energy, and they both have zero kinetic energy. Then we start to accelerate the ring up, so the ring gets some kinetic energy and also starts to gain some potential energy, which is lost in the potential energy of the spring. Okay, and you can see the ring really gets up pretty high, and since the ring gets pretty high, its potential energy is high. So yeah, wow, a lot of stuff going on here. But I think the important part is that we can actually see here, look, this actually stays constant until this point right at the end where we actually hit the ground and we stop, we abruptly stop the rod at that point. So that's why there's that little dip there. So this looks pretty good to me.
Yeah.
I wonder what will happen if we actually zoom in on it. So let's zoom in on that total energy and see what that looks like.
Well, it wiggles around a little bit.
It does wiggle around a little bit, doesn't it? And if we keep on zooming in,
Oh, look at that.
yeah, huh. So does that mean our simulation's not working?
Well, it could be numerical issues here.
Yeah, I think this probably is a case of numerical issues, but there are a couple things you can see. One is you can see stuff is actually bouncing around a bit. And you can also, if you look closely here, you'll note that we're actually, whoa, come on back here, you thing. The energy's actually dropping as well,
Yeah.
right? So as you can see, energy isn't really conserved in this simulation, and the reason it's not really conserved is we're not actually solving the differential equation exactly. We're doing a numerical approximation to it, and so but if you see things like this, right, and you tell me energy is not conserved, I'm going to look over at this y-axis and say, wait, 899.94 up to 900.06 looks to me like energy is conserved. Okay. Cool. So that certainly gives us some confidence.
Yep.
Should we look at that for the skateboard too?
Sure. Do you want to look at the code for that? Probably no need.
Yeah, we can look at the code for that. Where's the code for that? Let's see if we can find it.
Hopper energy. Yeah.
Hopper energy conservation check. Right, so you can see here, we're looking at the code, we're calculating kinetic energy of the two masses, right? Potential energy of the two masses, you'll notice we use 10 for 9.8 here because we're lazy. And then the potential energy of the spring is 1/2 k times delta x squared. So all of these energies look like they're following that same type of sort of framing that we thought of before.
And if you don't happen to remember what the sixth element of your state vector is, you could probably create a variable there with a more meaningful name.
Yeah, if I were a better coder, I would have done that.
Well, there you go. All right,
So, but you'll notice that I did do a good job of actually labeling everything down here.
that's nice.
So you should be proud of me for that,
I'm
Jason.
totally proud of you, Mark.
Okay. All right, and we can also do the similar thing with the skateboard. You guys have actually seen the results of that previously, so we'll,
Oh, yeah, they're on the poster, aren't they?
yeah, they are, so. And this is actually a case where we sort of exploited both the energy conservation and the fact that we've got this animation to kind of make this hybrid validation. So you've seen this before with the rider kinetic energy, rider potential energy, ramp kinetic energy, and total energy, and what's actually happening with the rider at different points along the way.
Mm-hmm.
Or these are just keyframes that are pulled out at different times and are marked. So this certainly was a sort of piece of code that took a little while to write because we had to create all these different things in different places and make all that work, but it was definitely worth it in terms of being able to put something on that poster that made sense.
Mm-hmm.
All right, so what else should we do? I think we need to do something that causes people to ooh and ah, don't you?
Wait. P color.
We could do a P color.
Yeah.
How about if we combine a P color with animation?
No.
An animated P color.
Are you serious?
Would that make your head explode or what?
My head would
I think
explode.
it might. It might make my head explode. But actually what we're going to show you now is actually a pretty useful thing. It was actually a pretty critical piece of code in trying to figure out what was going on with the skateboard.
There's the P color.
So here's the P color. So what we're actually plotting on this P color is the mass ratio, so ramp mass to rider mass, versus the velocity of the rider. So each point corresponds to a different velocity and a different mass ratio. The color here actually tells you how long the rider is on the ramp. So like here in this region, the rider is staying on the ramp quite a long time. And then this contour actually shows you the region where the rider successfully completes the trick. And you might wonder why this thing is like following the mouse around. Well, that's because we set this up so that when you click on a given value here, it actually runs the animation for that combination of parameters.
Whoa. My head is exploding.
So, and this is quite handy. It took a little while to get this to work, but it allowed us to really check to make sure that the simulation was doing what we thought it was. So for example, our conditions for success versus failure, we really were able to check and say, okay, that was a success that we just did. Let's try over here and see what happens there. Right? That should be a launch off to the right. And sure enough, there it
There you
goes,
go.
launched off to the right. Right, if I come over here, I'm gonna roll off to the left or launch, I guess that's why I launched left. And as you can see, particularly since we're currently videoing this is kind of excruciatingly slow, but it does actually allow you to understand what's going on really well. This is actually the thing that allowed us to figure out what was going on in this region. And here, where you'll remember on the presentation, there was kind of this funny speckling going on.
Mm-hmm.
Well, in that region is where you tend to get these sort of multiple oscillations, and they're quite hard to actually hit. I don't even know if we'll hit it on this one, but we'll see. It's very exciting to
Look at that. All
wait
right.
and find out whether the multiple
Come
oscillation
on. Go.
will happen.
Oh, yeah.
Oh yeah.
Look at that.
Oh.
It's going up. And down.
Oh, back down again.
Wow.
Oh, this is so exciting.
We're not going to give them the code
Wow.
for this, are we?
I think we might give them a code for
No.
this. Yeah, I think
Don't.
we might. Oh, but I think we're going to launch off to the
Ah!
right. Ah!
Oh, well.
So, anyways, certainly this is the most complex piece of code that we wrote for this, but it was the piece of code that actually allowed us to figure out what was going on. So it's worth thinking about doing this type of thing, particularly if you have sort of complex behaviors that you don't understand as well. This sort of combination of things can give you a lot of insight. So all this code is on the website.
Yeah, we'll put it on GitHub too.
And on GitHub. That's what all the cool kids use, I understand. So you're free to look at it. We will give you the caveat that this code is kind of a little clunky in places. because I wrote some of it and I was not.
It works and it's awesome.
It works and it's awesome. It's just a little clunky. So with that, thanks very much and have a great Thanksgiving.
Bye-bye.
Bye-bye.